So here's an example where we had to find the stiffness in a spring when it's suspending a crate, as you can see in this picture here. Typically when we have a spring problem like this, we use the force equals the spring constant times the stretch length of the spring formula that you see here. So when you have a problem like this, the first thing you want to do is generally draw a free body diagram, which we have down here. Our X and our Y coordinate system is well defined. We show that they had the crate going perfectly down our Y coordinate, and we have our weight calculated here, which was the 40 kilogram crate times our force of gravity, which was 9.81, and we just have all our dimensions, and then our two unknowns is our tension in this dB suspension here, and then the tension in this DC suspension here. So when it comes to this, we need to find the tension force for this one, so we can plug it into back into our original spring equation here, and then solve for this K constant. So the best way to do that is to use the summation of forces in the X and the Y direction, and then to solve for our two unknowns here. So we'll go ahead and start setting that up. As you can see, we just use a traditional Cartesian XY system. So in this case, this tension is going, dB is going positive in both the X and the Y direction, while the tension in the DC is going in the negative X but positive Y direction. So I'll just start with our summation of forces in the X direction. So I like to annotate the direction that I'm using as positive, which in this case is left to right. So we have summation forces in the X. Now just taking a look at this, starting with our tension, this dB force here, we're going to go ahead and use this our triangle coordinate system, where we have an X component and a Y component, and then a hypotenuse from that. And we got that by using the dimensions that were given to us in the drawing. As you can see, we have a dimension of 3 meters and then a height of 2 meters. So we just plug this into our triangle here, so that gives us an X component of 3 and a Y component of 2, and then the hypotenuse is the square root of 13. So in this case, since this tension in dB is going into the positive direction, we'll use our X component here, and then divide it by the hypotenuse, and then multiply it by our unknown force. So we have 3 over the square root of 13 times our unknown tension. Now if we look at our second tension over here, that's DC, going from point D to point C, we'll see that this is going in the negative X direction. So we'll have a minus sign here. And then once again, using these dimensions, we were able to come up with this triangle system, coordinate system. So our X and Y coordinates are both 2, and the hypotenuse is going to be a square root of 8. So we can use the X component here, which is 2 over the square root of 8. So what this does is it just allows us to use these X and Y components, and we don't have to find the inverse tangent to find the angle here. It just makes this a lot easier or quicker. And then we'll multiply this by our tension going from D to C, and that's going to be equal to 0. Now I'll set up our summation of forces in the Y direction. So my positive direction is going up. Now starting with our tension in dB here. Once again, we're going to use this triangle system. So our Y component here is 2, and then we'll divide that by the hypotenuse, which is 13. So we have 2 over square root of 13 times the tension in dB. Also, just to reiterate that both these vectors are going into the positive y direction, so they'll both be positive. And then the y component here is 2, and then we'll divide that over our hypotenuse, which is the square root of 8. So 2 over the square root of 8 for our tension in DC. Now, we have this this crate that's getting pulled down and perfectly centered in the y direction. So since this is a negative value and our summation of forces is equal to 0, we can just go ahead and add this to the end. So it's going to be equal to positive 392.4. So now here you could now you just use some algebra. You can either substitute or if you have like a matrix system set up in your calculator, you can use that to solve for our unknown tension forces here. So I won't go over that. This is just a lot of algebra. The answers that we get is the tension from D to B is equal to 282.96 newtons, and then our tension from T to C D is equal to 332.96 newtons. Now we have the force for our spring formula here. Now we need to find the stretched length of the spring. Since we're given an unstretched length of 2 meters, and we know that the entire length of this tension here is the square root of 13, we can find the length of the stretched spring by just subtracting this total length of the square root of 13 minus the unstretched length. So let's call this delta x, and that's going to be equal to the overall length of this support here minus this unstretched length, which we can call L naught, and then that's going to be equal to the square root of 13 minus 2, and that gives us a stretched spring length of 1.605 meters. So now that we have this delta x value, we just need to solve for k. So we can rearrange this equation by making it force over the stretched length of the spring. Then we'll use this force value that we got here and plug it into our numerator. So it's going to be 282.96, and then we'll use this spring length here, the stretch spring length. So it's 1.605, and that gives us a K constant or stiffness value of 176.24 newtons per meter. So like all the other examples, it's imperative that you have a decent free body diagram like what we have drawn here. It really outlines your dimensions, and then it can help you set up this triangle coordinate system that makes these calculations go quite a bit quicker, so you don't have to worry about finding the sine or cosine of certain angles. Just remember your positive directions for your x and y coordinates, and typically and then just find the one negative value. In this case, it was the weight in this y direction. That will help you that'll turn into a positive value for your answer here. And then once you solve for the two forces and then unknown forces, and then you can, in this case, use that force to find the K constant of the spring.